Good afternoon. Welcome to the Center for Imaging Science seminar speaker. For those of you that don't know me, my name is Dave Messenger, Director of the Center. And I'm very pleased to welcome our seminar speaker today, Dr. Julia Dupuis from Physical Sciences Incorporated. Dr. Dupuis joins us as I said, from Physical Sciences Incorporated, which is in where, Massachusetts? Andover, Massachusetts, where she's the Vice President of Tactical Systems. She has a long history of developing novel imaging systems for a wide range of applications. She did her PhD in electrical engineering from Boston University, although she said it was mostly optics.
Oh, yeah.
And she also has a master's in EE from UMass Lowell and a BE from Dartmouth and a BA in physics from Colby College. So please join me in welcoming Julia Dupuis.
Thank you very much for the opportunity to present to you today. So I thought I'd start a little bit giving you a little bit more background about myself and my professional path and the kinds of things that I work on. I've spoken with a number of you already today, so sorry if some of this is a repeat. But I've been working at this type of job for 23 years now, so I've been in this game for quite a while. I was at a small company pretty close to Andover, Mass. For 16 and a half years that I started right out of my bachelor's program called Optra Incorporated. And then I moved over to PSI about 6.5 years ago to continue my technical growth. Basically, I was looking for a new challenge and a bigger pond to swim in, quite frankly. Here are the things that I've been working on over the past 23 years. So really the common core of this is I've been working on new technologies with an emphasis on rugged fieldable sensors to meet generally new DoD applications, new and challenging applications. So the majority of my work has been in spectral and hyperspectral sensor development, targeting solids and liquids on surfaces and vapor in the far field. I've done some work in infrared thermography, Raman. Recently I've been working on some LiDAR systems employing some compressive sensing techniques. PSI has our own drone that we manufacture and we sell to the armed services. So we've been finding all sorts of things that we can mount to that and fly around. So we've been doing some point chemical and biological detectors that we've been flying into potential threats to do a confirmation. And then early on in my career, and then again recently, I've gotten into back into DMD-based scene projectors. So those are for training infrared threat detection systems with realistic scenarios without doing flight testing. So that's a low-cost version of it. So here are some pictures of some of the technologies that I've developed. This is a low-cost open-path FTIR spectrometer. Something else that I've paid a lot of attention to is how to engineer out the high-cost components in conventional systems. So the system had a couple of design economies that were allowed by the specific application that we wanted to solve. So this was specifically measuring large molecular toxic industrial chemicals where you don't need super high spectral resolution in order to do good spectroscopy. So that's an example of one design trait. And then that lets you do things like use an uncooled detector because you have better signal to noise, for example. So understanding all of those trade spaces is something that I think we do pretty well. Here's the infrared scene projector. So this actually has 2 DMDs to project into mid-wave bands, and there are some images that we did out in the parking lot of my old building. And here's one of the latest things that I'm working on that I was hoping to speak about today, but I don't have the go-ahead from the Army to go public with this yet. But this is a long-wave infrared hyperspectral imager based on compressive sensing in a single pixel architecture. So this sensor has a tunable Fabry-Pro filter and then a DMD and a single element detector that we couple all the light onto, and we use compressive sensing techniques to reconstruct images. And the point of this system is we've eliminated the high-cost infrared focal plane array that need to be used by any kind of conventional long-wave hyperspectral imaging system. We talked a little bit about my background. I just want to mention that my MS and PhD I actually did part-time. And the reason was really just that I was very engaged in this kind of work. I was doing numerous projects that were equivalent to a PhD thesis. I found basically an advisor in the Boston area that was interested in working with me and having an industry person in the lab kind of accelerating the rest of my lab mates to do things a little bit differently and a little bit more quickly. So I was going to talk about a little bit of that today. So a little bit on PSI. So we're a 46-year-old company. Our revenue across the whole business, including 3 subsidiaries, last year was $70 million. This year we're projected for 80. We have about 200 people. About 100 of those are PhDs in hard sciences, engineering. We are 100% employee owned, which is fairly unique. So we all basically have stock in the company and a collective interest in seeing us succeed and grow and do pretty well. Here's what we work on. So it's really applied R&D for the government and the Department of Defense largely. A lot of our R&D budget comes from the DoD and the various different armed services. We are really trying to develop technology that can go into the field and go into potential acquisition programs. We're not happy when our sensors just sit on a lab bench or go into a cabinet after we're done. We're really driving at finding new things to use and really tightly sticking within requirements of applications so we have something in the end that solves a real problem. Occasionally, we become basically an IRAD arm of some of the large contractors, large aerospace contractors like the Lockheed Martins, who don't really always have that capability in-house, so they will pay us to develop a new capability when they're looking at some acquisition program and they want to have some kind of sensor in place in the next several years. That's something that we've done before. And we do low-level manufacturing, especially in certain areas of the company, and direct sales. So here's a split up of where our funding comes from. Here's a pie chart of our product areas, and you can see a lot of these are under the name of sensors. So we do sensors for DoD applications. We actually also do a certain amount of work for the NIH with medical sensors. Standoff sensors, we have some laser development, and then we have some people working on materials and also algorithms. Here's an org chart. I won't get into too much of this, but basically the way we're structured is we have a large number of R&D groups that each column is a separate enterprise. 2 of them are subsidiaries on the 2 ends. And then these are the R&D enterprises within PSI, and this is where I reside right here in the tactical systems. And then I'm still running an area called optical systems technologies that most of these sensors that I'm going to be describing were developed under. And then we have a few other technology groups that are higher up on the TRL scale and are developing capabilities that are actually getting fielded and sold in some level of volume. So that's these green boxes over here. So here are the things I'm going to be speaking about in the next 30 minutes or so. So we'll start with just a really brief introduction to hyperspectral sensors so we're all on the same page and understand what I mean when I say hyperspectral imaging. I'm sure a number of you have been exposed to these various architectures, but I just wanted to provide a definition. I wanted to walk through a couple of applications and associated signals. So I was asked during lunch, what are the applications for hyperspectral imaging? So I'll give you a few examples and go through, what are the discriminant signals that we're looking for? What are the challenges of each of these applications? And I've actually ordered them from, in my mind, the easiest to the hardest in terms of the spectroscopy. We'll go through a couple of hyperspectral sensor modalities, just different ways of splitting up light and forming an image, and why you would choose one over another based on a given application. And then my goal is to walk through a couple of design examples where we lay out requirements, understanding what the application is, writing down the system requirements, understanding how the sensor performance plays into those requirements. And it seems like this general practice is taught here, which I'm pretty excited to see. That wasn't necessarily my experience in grad school, but the procedure is very important. You want to design something that is meeting its intended application and not just selecting components and seeing what they do when you put them together. So we'll walk through 2 of those and then just a brief summary. So here's the definition of hyperspectral imaging. This is really all I mean. is a sensor that generates tens to hundreds of spectral bands over an image, producing a data cube in any portion of the spectral range. So this could be in the ultraviolet all the way through terahertz. These measurements can be passive using ambient radiance coming from the sun or the target's self-radiance. You can use that for spectroscopy. You can use active illumination with a laser source, and that comes with high sensitivity, but other problems, speckle being one, and I'll talk about that a little bit with a second design example. These are the applications that I'm going to walk through. So vapor plume imaging, which I would say is from a spectroscopic standpoint the easiest thing to do. The next is surface mapping target detection, so you're just trying to understand what a surface is based on its spectral properties. And then the last one is when you have something on the surface and you're trying to detect, the obvious situation is you have a white powder and you want to know what it is, and you don't want to get too close to it, you don't want to sample it, you want a really quick sensor that's just going to tell you what it is and how to deal with it. Then I'll walk through these modalities, going through a push broom dispersive spectrometer, interferometric systems, and then some emerging systems, including coded aperture systems and single pixel architectures. So starting with standoff vapor detection, so this again I will argue is one of the slightly easier things to do. So this is passive hyperspectral imaging. I'm talking specifically about the long wave infrared where you're probing fundamental vibrational bands. So this is the fingerprint region. Molecules have fingerprints. They have very specific spectra that you can use to identify what that plume is over there in the far field. And this is basically how it works. You have a sensor looking at, we'll call this a background. This could be the sky, it could be a mountain, it could be a tree, and then you have this plume in front of it. And it turns out you can see that plume if there's a temperature contrast between the plume and the background against which you're viewing. And this is how long wave spectroscopy works. And it turns out that it doesn't really matter if the plume is warmer than the background, then you see these features in emission, lines go up. If it's colder than the background, then you get absorption, the lines go down, basically. But the detection algorithms can handle it either way. And in general, with the exception of the colder or warmer part, these spectral features are pretty invariant. They don't change a lot with temperature or illumination condition or any of that stuff. As long as you're not specifically looking at absolute radiance. So I should mention, in most of these applications, I'm really interested in target detection and identification and false positive mitigation. If I can do that without absolute radiometric calibration, I will do that. And that's kind of what we're talking about here. This is kind of an example of what some features look like for chemical warfare agents. So you can imagine that you can discriminate between these using, honestly, fairly low spectral resolution. The bands are pretty broad. You get better signal to noise if you're not, dividing your light into really, really thin spectral bands. And here's, after running detection algorithms, what you can get out of them. So in one of the examples later, I'll walk through how we do target detection in a cluttered environment and how we handle background pixels. But what we're going for is taking the data in and doing an automated detection algorithm that first determines what are background pixels, then finds target-containing pixels, and then tells you what's in the target. And this is some example data from one of PSI's sensors that's imaging long wave infrared using a Fabry-Pro, not the compressive sensing one, but a conventional focal plane array. And we've actually done a lot of field testing out at deadweight proving ground, doing just imaging chemical releases of various different stimulants, and that's an example of what you would get out of this system. Okay. So the next application is passive hyperspectral imaging when you're looking at a surface and you're trying to detect a target or map vegetation, for example. So target detection can be done in the long wave or sometimes the short wave or near. Long wave, you need the thermal contrast again that I had mentioned with vapor, so you need some difference in temperature and or emissivity between the target you're measuring and everything else in your scene. But the nice thing about it is you can do it at nighttime because you don't need the sun for it. So in some cases, things work better at night. And there's veneer smear, which you're looking for pigments and materials or sometimes molecular overtones. That requires obviously solar reflectance, and that's daytime only unless you bring your own source, and then it becomes an active system. That gets hard to cover large fields of view. So here's the bare minimum that is required to do long wave passive hyperspectral imaging of surfaces. So you need the temperature contrast that I mentioned. Often we use cold sky background, so your surface is basically just emitting radiation, and you get a good temperature contrast between the surface and the sky in which you're looking at a reflection from. So that's one way of doing it. Usually works pretty well. It doesn't give you the best sensitivity and doesn't work indoors or when it's really cloudy, but it's definitely a good approach. You need to be able to separate the temperature and the emissivity of your targets, and that's not simple. There's a lot of algorithmic approaches to that. And you need atmospheric correction in some cases, depending on what part of the atmospheric windows you're covering. So, these long wave systems tend to reside down here. But as you get kind of closer to 14, you need to start accommodating for some of these bands. Visible near-IR SWIR requires, like we said, solar spectral radiance, but you need to be able to calibrate it. And I've talked to a lot of people here today about the best way to convert your hyperspectral data to absolute reflectivity units. And that's very difficult. You need extra sensors to make a good measurement and calibration, or you need some other good way of doing that, but it's very difficult to get highly accurate absolute reflectivity across your field of view. And then the atmospheric correction, and there are even more bands down here, and frankly there are portions of the spectral range that you just can't see anything through because there's no light. Here's an example of passive vegetation mapping. These are the types of signatures that you might be looking at. So again, they're not very fine, they're fairly broad, and you're looking for key features. It depends on what you're trying to map, but if you're looking at the difference between alive and dead, you can tell a lot from this spectral range right here, and the sharpness of this red shoulder, and also the chlorophyll peak that makes plants green. And here's an example data product that we generated with this hyperspectral sensor that we developed at PSI that just shows a spectral angle map. So that's just every pixel in the image, how well does it map to reference spectra for healthy vegetation versus dead vegetation. And that is basically colorized based on that. So that's something else that you can do with this technology. And in my mind, this is one of the hardest things, at least that I've worked on in my career, and this is active hyperspectral imaging in the SWIR long wave via spectral reflection. So I say active because this is very difficult to do passively. You don't get a lot of signal to noise. It, passively doesn't work inside. You tend to use sources, like I've done a lot of work with quantum cascade lasers, and I'll give you an example later in this presentation. ICLs in the midwave. Some people have been working on supercontinuum. The idea is just you're almost sending a highly directional light bulb at the surface. And the receivers tend to be spectrometers or imagers if you're tuning the laser, and that's another way to do hyperspectral imaging. Typically, these aren't technically hyperspectral imagers because they tend to be raster scanned to build up the image. The example I'm going to give you later is truly an imaging system, but typically you need power densities on the surface that are inconsistent with flood illumination. So that's just a fundamental limitation of most of these optical sources. You can't cover a large spectral range and get good performance, so we tend to raster scan. Speckle becomes an issue as soon as you brought in a either or both spatially or temporally coherent source. You have a new noise source called speckle. And that's something else that you need to beat down in order to maintain your detector noise limit or whatever detection limit you need for the targets that you care about. So that's something that I'll get back to, and how you beat down speckle in order to preserve the fidelity of your measurement. This type of measurement is difficult because the spectral features are highly dependent on how the material is put on the surface. You could have a thin coating of it and the light would go, and here's some examples right here. If you have a coating on your substrate, the light could go all the way through and come back out again, or it could be so thick that you only get a first surface reflection, and you can do spectroscopy on the Fresnel reflection as well. It has shape to it. You can have particles on surfaces. You can have subfilled pixels where you get a substrate contribution. You can have particles that create scattering that have their own spectral shape to them. So what happens in these cases is you end up needing a larger family of reference spectra so you can recognize, TNT on a surface no matter how it was put on there. And that's pretty important that you have these advanced physical models that reflect what it looks like, and your spectroscopy can then recognize it. So that's something that we've done a lot of work in here. These are some examples of 2 different measured spectra and 2 different physical models fit to it. And we basically do an F-test to see which one fits better, and we pick that one and say that's the material. Again, you can generate a detection map, and here's an example of one of our raster scan systems, which is why this looks like it's going up and down. And in this case, we had TEP on a surface, and we're able to detect all the droplets. All right, so here are a couple of hyperspectral imaging modalities. The first is a conventional push broom dispersive spectrometer. So I would guess most of you are familiar with the head wall sensors system, where the idea is that you're looking at a strip on the ground that gets imaged onto a slit, and as you advance over the ground, you build up a hyperspectral data cube by covering these different strips. At each position, the light is coming through the slit and is getting dispersed onto a focal plane array, which captures wavelength in one direction and a long track spatial resolution in the other direction. So this has been developed. They're widely commercially available. A number of companies offer these. Sometimes you can incorporate an internal scanning mechanism, which is something that we did at PSI and I'm going to be talking to you about. That lets you not depend so much on the aircraft motion and get slightly better data, or in some cases much better data, because you don't really need to know where you are. You can just stay in one place and scan the ground. So characteristics, typically these are done in the veneer SWIR, owing to the ability to get low-cost focal plane arrays. These are not expensive. Even InGaAs is much cheaper than the long-wave focal plane arrays that I get for my long-wave systems. A number of companies are making these, and it's not super hard to get really good signal to noise, because if you're doing this right, you should be shot noise limited. Throughput is not as much of a problem, and when I say throughput, I mean the centimeter squared per steradian product, not radiometric efficiency. So it's really the light gathering capability of the system is lower in these particular architectures, but you don't care because you're not readout noise limited. You should be shot noise limited. You have this bright sun shining on the ground. This isn't super difficult. But one thing I'll add is that usually you run into a full well capacity problem, and that's limiting your shot noise. So when you're selecting your focal plane arrays for this type of sensor architecture, sometimes bigger pixels and fewer of them are better than small pixels, because you can integrate more and you can basically get a better per frame shot noise limited signal noise. It's something to pay attention to. So the next one is interferometric. So in this case, an image of the scene is basically just formed through an interferometric element. So these are the different types of architectures that I've come across. There's the tunable filter, and this is PSI's conventional standoff chemical agent detector, where you basically form an image of the far field through a tunable Fabry-Perot filter, which is basically a spectral filter that changes with plate separation or with mirror separation. And if you control this very carefully, you can get band sequential data recorded by a focal plane array back here. You can also do it with AOTF or liquid crystals. There are even some of those that operate in the long wave. The next is a Fourier transform infrared, and this is actually a visible version of it, but the idea is that you form an image through a Michelson interferometer, and every pixel in your focal plane array captures an interferogram, and you can create spectra from that. So that works pretty well, but you need a moving mirror for it. It's a lot of data. It's a lot of out-of-band data because you have to completely sample it for Nyquist criteria. Here's another architecture that PSI has been working on, which is a spatial heterodyne spectrometer. There are a number of things we like about this. It does require a focal plane array, but the way you think about it is it's a tilted Michelson interferometer where you've replaced the mirrors with gratings, and what that does is it creates a spatial fringe pattern that you sample with a focal plane array. The heterodyne part comes from the fact that these gratings are tilted about their literal wavelength. So one wavelength has a 0 fringe frequency, and then everything else scales from there, and that limits the number of pixels you need to properly sample it. So it's kind of more efficient in terms of that. And it is technically a push broom architecture, but it has 2 orders of magnitude more throughput than a grating system, because all of your light from every color goes onto the full focal plane array. So you just have way more throughput. And what this lets you do is it lets you capture spectra at the frame rate of the focal plane array. So you can do snapshot imaging along one dimension at least, and then gather the rest by either the motion of the platform or with a scanner. But it lets you get very, very high data rates and a lot of throughput and very sensitive measurements. So this is an architecture we've applied to some of our surface detection applications pretty successfully. Go back to sensitivity. So again, these are most common in the long wave infrared spectral range. I think there are a few reasons for it, but the main reason is in this regime you should be detector noise limited. Your signal doesn't have significant shot noise relative to the noise of the detector itself. Throughput or ATON-DO is at a premium. Your signal to noise scales directly with it, and in most of these applications your discriminant signature is pretty weak, so it's very important that you get as much sensitivity through the sensor as you can.
Julie, real quick.
Yep.
These seem to have different spectral bandwidths associated with them, is that correct?
It depends on how you design them, yeah. So, you mean dispersive versus
Well,
these
like I said, a
architectures?
Pro has a pretty short free spectral range, for example. Are you operating within the free spectral range?
So, yeah, we operate the chemical agent detection system in 2nd and 3rd order. So, the free spectral range, and we're trying to cover the 8 to 12 micron range. So it's broad enough to work without order confusion. It's not super high resolution. We run it at about 8 wave numbers, mostly because that's all you need to do chemical agent detection. An FTIR obviously can have higher resolution, but the ones I've worked on, we specifically designed for lower resolution against these applications where we don't need the high resolution. So yeah, there's certainly resolution constraints to it. In the Fabry Pro, you can operate it in a higher order and get better resolution at the to sacrifice free spectral range. We've also tried to in tandem as well to extend the free spectral range and get the resolution at the same time, but that becomes pretty expensive.
Okay.
All right, and then here are the emerging architectures. So this architecture was developed at Duke. It's a coated aperture snapshot hyperspectral imager. I haven't specifically worked on this type of architecture. I just wanted to present it for completeness, but the idea is you form an image on your coated aperture mask, and then you go through a dispersing element, and you collect this image at the focal plane array that you need to reconstruct to create the hyperspectral data. So you're definitely sharing spectral resolution, spatial resolution, real estate on one focal plane array as part of the trade-off. There are also single pixel cameras, so this architecture was developed at Rice University. You can imagine putting a tunable filter in front of this, which is one of the things that we've done. But the idea is to form a scene on a spatial light modulator, notably a DMD, that you use the DMD to impose a measurement basis on your image, and sample through a number of measurement bases, and then you can do a reconstruction in a sparsity basis in which your image is basically sparse or doesn't require a lot of coefficients to represent. So what I like about this is it eliminates the focal plane array. It provides inherent data compression because you're collecting compressed data. You're not collecting high resolution data and subsequently compressing it. So this is kind of interesting. Both of these architectures are pretty computationally intensive, require a pretty good processor to do these reconstructions. So it's one of those things where they've traded off complexity in hardware to do it in software, which I'm in favor of, but it makes the math a little bit more difficult, and it's never free. And we're still working on, what really are the noise ramifications of your detector noise versus reconstructed noise, and where do you land on that once you're back in image space. Okay, so I was going to go through the first design example. Is the Veneer shortwave infrared hyperspectral imaging sensor. So this opportunity was not brought to us, but it was published in a Department of Energy SBIR, Small Business and Innovation Research book a few years ago, and I wrote a proposal against it and got an award. Specifically, they wanted to fly HSIs in a steering mode on a rotary wing aircraft. So they didn't want that cooperative motion between the aircraft and the framing of the hyperspectral sensor. And basically, they wanted pretty broad spectral range, so Veneer all the way through SWIR out to 2.5 microns. And they wanted to measure these vegetation features over a 30-degree field of view with, in this case, better than a 30-centimeter ground sample distance at a maximum altitude of 400 feet, which is basically as high as you're allowed to fly within FAA regulations. So, we looked at a couple of things here. Basically, we started by fleshing out what are the capability-derived KPPs. So KPP stands for Key Performance Parameter. What does the application need? And this should be, in theory, agnostic to the sensor you develop. Really, what does the application require? This is where you need to start. And then you derive what your sensor needs to be able to do based on those capability KPPs. In looking at these and the hovering requirement here, the takeaway is they really weren't looking for a conventional push broom system that you had to fly over, and they wanted to be able to fit a lot of capability in one box, while providing good image quality from a hovering aircraft. So this is what we proposed. Here's the sensor right here. It's relatively compact, so it came in below 15 pounds. Veneer SWIR hyperspectral imager. We flew it on, this was our drone that we bought under the contract. It's made by Free Fly. It's called an Alta 8. Can actually carry up to 20 pounds. But our 15 includes onboard, single board computer, and all communication hardware to a custom developed ground control station. So there are a lot of other things in this box, and like everything else, once we built it, we learned a lot of things about how we would lightweight it the next time around. But this is what it does. It's a dual channel system, so it actually has two gratings, two focal plane arrays. One covers the Veneer spectral range, basically an octave, and then the SWIR spectral range, and we stopped at 2.4 because there's not a whole lot to look at past there. The key innovation is using the DMD as an agile scanning slit. So again, this gets rid of the requirement to fly over your ground. We're basically hovering and scanning the ground with the DMD, and I'll show you how we do that in the next slide. Here's what the data product looks like: 384 by 290 spatial by 480 spectral, quasi-calibrated, and we've been doing some orthorectification, spectral reflectivity data cube, and we can collect that in just under just over 2.5 seconds. Really, we were driving at a pretty high acquisition rate and the high data quality from a hovering platform. So here, just to get into more detail on the key enabling features. So it's really the DMD-based dynamic spectrometer slit. So this is our optical layout here and how this works. We form an image onto the DMD, And then the DMD basically just lets one strip at a time through with each frame and basically marches the dispersed spectra across the focal plane array, which is here, and then the sphere is up here. And that's how we collect the data. It lets you do a couple of things. It breaks this interdependency between aircraft motion and frame rate, spatial resolution. You can revisit parts of the ground that you want to go to. You don't necessarily have to fly over it again. One thing we realized is you can turn all the micromirrors off and take a straight light measurement and subtract that from all subsequent frames, which you can't really do with the conventional push broom system. So that makes really nice low background spectra at the penalty of dynamic range, because you've got that always sitting on your signal and shot noise associated with it. There are no macro moving parts. I don't count the micromirrors flipping back and forth as a moving part. And again, I think I've driven this point home already. So I know this is a big table, but this is how we connect the application-derived KPPs to the sensor-derived KPPs. So based on all of the system KPPs, this is what the sensor needed to be able to do in terms of internal field of view, spatial format, acquisition rate, and so on. So I won't go through all of these in a lot of detail, but this is the kind of design process that we do when we're trying to, we intend to develop a design and a capability that meets the customer's applications. Radiometric modeling, a number of you are doing this right now. But basically you need to figure out, how much light are you collecting? What are the number of photoelectrons coming out of that? And then figuring out the shot noise associated with your signal and also the background in some cases. And then you also need to accommodate readout noise. So this is really, can we develop a sensor with adequate signal to noise to measure the reflectivity modulations that we care about to tell the difference between certain types of plants or certain, the health of a plant, for example. So this is what a model would come out with. So this is actually taking solar radiance and putting it through the signal model. And there, it's a little bit more nuanced than this, but these are the main steps to figure out, is this design meeting my requirements for sensitivity? There's a lot of interdependencies between the KPPs, the derived KPPs, I should say, and what the optical parameters are. So I put together this spreadsheet that basically put the KPPs in yellow, and then, labeled in red here, and then the optical design inputs are in green here. So this spreadsheet basically helps you figure out what magnification you need, what focal lengths and lenses you need, what grading pitch you need in order to meet all of your spatial and spectral resolution requirements, your field of view, all of that. So this is sort of, as things changed a little bit, as we found, some commercially available lenses, what happens to the overall performance, and we could go back and forth with the optical design. So once the system was built and integrated, we always run through functional tests to see, is the system performing as we would project from our performance models? Is it working like it should be working before we take it out into the field and fly it, or measure vegetation or whatever we do? Again, a sea of numbers here, but what we were trying to do is use lasers to create solar irradiance levels on a target board, which turns out is pretty difficult to do with anything other than a laser, although I understand you're doing it downstairs with the integrating sphere, which was impressive. We use lasers in different parts of the field of view, and basically, the takeaway is at the correct solar radiance levels, we're meeting the signal to noise that we expected based on our models. This is just a measurement of the spectral range, so this kind of shows, the red is, Air Force data for spectral irradiance, and then the black is our data, and it kind of shows it's not yet field flattened or spectrally flattened, but this shows what we're able to cover and what we are sensitive to detect. Spectral resolution, again, we use the lasers at different parts of the field of view and measure the full width at half max of the response. In this column, this was a veneer laser, this was a SWIR laser. You can see we're losing a little bit of our imaging performance in the SWIR. We knew that was going to happen to some extent just based on the very broad spectral range of the optical design. This was very, very challenging in this case. But these were the types of numbers that we were measuring. Basically, we were aiming for about 5 nanometers, so we were doing pretty well in the veneer, and around 10 in the SWIR, so we were missing a little bit. But basically, we came away from this saying we have enough to resolve the spectral features that the DOE cares about, so we were going to move forward with it. So next I'm going to show you some field test data. So PSI is in Andover, Mass, but we have a off-site field testing location in Epping, New Hampshire, which is about 45 minutes away. It's predominantly used by our propulsion group that's creating new types of energetics, so there's some interesting things happening up there. But we can also take our drone up there to fly, and we can do some field tests of the local vegetation there. So this was really the first data set to look at the difference between live trees and dry grass. This was pretty late in the fall. And the takeaway, basically, the black is the good vegetation, the trees, and the red is the grass, which was pretty dead. And we see the general spectral features that we would expect, namely when vegetation dries out, it actually gets more reflective in the SWIR because it has less water in it. So that's one thing that you see in the red spectra, and then you also lose this chlorophyll peak, which is why it doesn't look as green anymore. So we're not really vegetation spectroscopists, but this was our sniff check on the data. Does it look like we expect? Does it contain the features that we would expect? And it generally agrees with what we see in the literature for vegetation shape. Then we flew it, actually after we collected all the data on the ground and it was safe to fly because we had fulfilled our contractual obligations, because this was a little scary in the beginning. So what I'm showing, actually, what I was showing previously and I'm showing again here this is spectrally summed SWIR channel and veneer channel. So this is just taking all of the bands and summing them up just to graphically, pictorially show what the data looks like. And then you can take any square and look at the spectra over here. But the takeaway here is we were really trying to look at the spatial resolution that we had and what do things look like if we're not correcting for aircraft movement. And you can see we're doing pretty good at resolving this flagpole here in the veneer and the SWIR, and we generally don't have a lot of motion-induced artifacts. We're not seeing blur much beyond about a pixel, so that we were pretty excited to see how well it does in a realistic environment. So we did a quick capability demonstration for the customer for vegetation mapping. So this is that SAM map that I was showing before. Here's the equation if anyone cares about it, but it's basically just mapping vegetation to 2 different types of reference spectra, one for healthy vegetation, one for dried out vegetation. And this is an example of how the data would get presented, where we've got the unhealthy vegetation in red, where it looks generally kind of dark in this case. I think this was the veneer channel that we're looking at here. And healthy vegetation in the green, and the purple is where we just don't have a good match to either one. So this was really meant to be a first order approximation to what the DOE cared about. And then the last thing we did was a capability demonstration for measuring disturbed earth. So basically we have a Navy customer that's interested in beach zone mapping, looking for things buried in the ground, namely landmines. So we did a capability demonstration where we disturbed earth and then patted it down again and flew over the beach zone and moved from the water's edge all the way into dry sand, and that's what this is showing here. This is the ocean end and the dry land. And this is the results of a really basic detection map that's doing a SAM and also some morphological transforms to look for blob-like objects, but you can see we were able to catch most of them. This was really meant to be a basic capability demonstration, and we're looking for additional opportunities to move the sensor forward against this particular application, because there's more people who want this than vegetation mapping, it turns out. All right, so the next example that I'm going to show you, and I'll try to get through this quickly, is so this is long-wave infrared hyperspectral imaging of surface contaminants. So this was a Department of Defense application where they wanted to look for chemical agents on a surface. They wanted you to walk up to a surface within a meter and scan an area and tell if anything harmful is there, and that would then inform what, how they would handle it, how they would suit up, what happens next. This application is interesting because probability of detection is very important. Low probability of false alarm is also very important. As you can imagine, you don't want these guys suiting up if nothing is there. They really can't do much once they're suited up. So it's pretty important that you have high confidence in your answer in this case. So here are the key attributes of our approach. We're using reflectance spectroscopy, so we're shining a laser at a surface. In this case, we did do flood illumination because we were close enough to the surface and had enough power that we could do it that way. Applicable to all material presentations. In this case, they were looking for large enough amounts of chemicals that we didn't need to worry so much about those advanced physical models. We are expecting for the most case to be an optically thick regime, which basically means we have to recognize the Fresnel reflection off the surface. But as an objective surface loading, we have to go into optically thin materials or potentially particulates. And we did speckle mitigation on this point, and the idea was to drive the speckle noise down below the detector noise limit so we can accurately do our spectroscopy. We used QCLs after a market survey because there really isn't that much that's available that's this directional and this bright to do this job. So, I've been looking for optical sources for a while to do this job, and it turns out QCLs are still the best option. Here's another KPP table split up between threshold and objective, and in this case, it was truly defined by the customer. This is a real DoD application, so we didn't really put these together the way we sometimes do for some of our opportunities where we really need to figure out the application requirements. So here's our solution. We have an external cavity tunable QCL that we project out to the target surface with an OAP, an off-axis parabola. This diffuser here is for speckle mitigation, and I'll talk about that a little bit later. And then we just image the surface with a microbolometer camera, and the ECQCL is wavelength tunable, so you step through each of the wavelengths that you care about, and that's how you collect your hyperspectral data cube. We have a discriminant signal to noise of better than 20 at all wavelengths using the active speckle mitigation. And then I'll talk a little bit more about our detection algorithm, which is a variant of the adaptive cosine estimator, and I'll go through that in a minute. Again, we came up with derived KPPs for our specific sensor platform in response to the system level KPPs. And here are some of the spectral reference spectra that we'd be looking to match. So this is the reflectance spectra. This is the optically thick regime where you only get a first surface reflection off of the top of the material. And you get these, basically this ends up looking like a derivative of the absorption spectra through the Kramers-Kronig relationship. So there's a physical reason for this, but you can do spectroscopy on that first surface reflection. And then this is the absorption spectra, and again, these are for the chemical agents that we cared about. But these signal levels together help define, what signal to noise we need and what minimum detectable reflectivity modulation we need. All right, so a little bit on the sensor design. So the configuration was designed to basically achieve the spectral range, the aerial coverage rate, which is how much, how many centimeters squared we cover in a given amount of time, sensitivity in concert with the receiver. So the QCL is made by Daylight Solutions. It's a Meerkat. It's a very big laser, but it does a lot. It provides over 100 milliwatts average power over the spectral range. And then here's a little bit about speckle mitigation. So speckle basically arrives arises from illuminating a roughish surface with a coherent source. So you get, these interfering, cells that basically look like noise if you can't do anything about them. And every surface is different, so you can't calibrate off of one and hope it's going to work for the next, because everything's going to blow up, and your signal can be pretty speckle dominated if you don't do something about it. So the first things that you tend to apply to speckle are temporal and spatial diversity. So the way you think about it is spatial diversity basically puts more and more speckle cells into your receiver field of view, so you get an averaging effect. And spatial diversity increases with your transmitter diameter, and also with your receiver field of view. Temporal diversity just generates more speckle patterns as you're integrating, and that's why we have that diffuser at the focal point of the OAP, is it's actually spinning, and it's reducing speckle, and it can show you data of what things look like with and without the spinning diffuser. And then basically what you want to do is you want to operate in a regime where one dominates, so in this case we're spatial diversity limited. So here's what it looks like. We have the laser going through a hole in the OAP, hitting the spinning diffuser, and then it scatters up into the OAP and then goes over to the target. And there's a little DC motor here that's spinning and creating our temporal diversity, which is much, much bigger than our spatial diversity. So this worked pretty well. We also have had a beam sampler here and a laser power normalization capability down there, so we knew at any given time how much power the meerkat was putting out. And then here's another signal to noise projection, assuming the microbolometer camera and letting the laser power vary, and also looking at different internal field of view or pixel coads, I should say, to figure out how we trade off spatial resolution with signal to noise as it affects the detector noise limit. And here's the expression up here that goes inversely with the sensitivity of the microbolometer. So a couple of details on our detection algorithm. So here's a flow diagram here, and there's quite a bit going on, and I'll try to be brief. In these hyperspectral images, a lot of the data is background. It doesn't contain the target you care about, but it's still important because it lets you do a pretty good in situ clutter analysis that becomes important in the ACE algorithm. So part of the pre-processing of before you actually do the detection is you need to figure out in the scene what's a background pixel and what's a target containing pixel or otherwise anomalous pixel. And that's what these steps do in our algorithm, is we actually first apply a SAM map against all of our targets, and that pulls out all of the pixels that contain only optically thick targets with no substrate contribution. And we kind of call out some pixels for our background pool. Then we do a target subspace elimination that basically figures out what other pixels in the scene look like they contain target or are otherwise anomalous, and those all go into our ACE algorithm right here to do a background, look at the background spectral statistics. The ACE algorithm does what we call an F-test, and what it does in this case is it looks at the different physical models for the different material presentations that we talked about. Optically thin film, optically thick film, a combination of the two, because sometimes you're in that middle region or sometimes you have particulates. So that's what this F-test is about, is looking for the best fit in each case. And then basically an answer comes out here, and we basically do a logical OR for a detect, and we can see in the various steps of our algorithms which pixel flagged on what part of the detection scheme is kind of interesting to look at. But we originally developed a lot of this concept for passive vapor phase detection, and we've added a lot of complexity onto it for the surface detection because it is, like I said, a much more complicated problem. Here's some functional test data on speckle. So what I'm showing here is just all of the pixel reflectivity values across the whole field of view. So it's taking 2 dimensions and converting to 1 dimension here. This is an infragold target, CARC-coated steel, which is a chemically resistant paint that is often used by the DoD, and then a white paint in aluminum. without the diffuser rotating, and you can see what happens with the speckle when you go down to your rotating diffuser. So basically, this is showing that our speckle mitigation is working pretty well, especially for a very rough surface that's primed to create speckle, like the Improgold right here. So I found that, you know, it's difficult to get rid of speckle. It's also difficult to form really good speckle. So the answer, you know, somewhat agrees with the model, but it's not, you know, perfectly predicted. So, you know, this NEP is about 0.2 is the variation on here, and then it goes down to 0.02. So that is enough for us to do our spectroscopy. Here's some developmental testing that we did. So again, we're looking at measuring chemicals on surfaces, liquid droplets. So we made a surrogate plate here with these different machined holes, so we could fill them with liquids and you know, test for different pixel fill factors. We had the 3 different materials. We had these 2 materials that I mentioned in the previous slide, and also high density polyethylene. It was assumed, again, everything would be optically thick, which is consistent with the threshold requirements. And then we tested these simulants, which are for these different chemical agents here, and then a solid here at the end. And then we had a fold in there because liquids drip if you put them upright. So here's what some detection maps look like. So this is testing against TEP on CARC, white painted aluminum, and HDPE. We had filled basically 6 of the wells, and as a first order, in most of these cases, we were getting detections on most of them. In some cases, especially in the CARC, the material was bleeding over out of the well onto the surface, and we got an optically thin detection in that case, which was kind of interesting. A few false positives. So this was what the spectral library was, and every time you see up here like a green, that's a false positive. We were having some issues with specular reflections off of empty wells. And then here's TBP down here on the bottom, and in some cases you get a mixed detection on certain pixels, and that's represented right here. But in general, you know, we were getting decent detection. In many of these applications, you don't need to perfectly map all over the surface where every bit of chemical is. You just need to know that it's there and what it is, and that that it's not something benign. That's what's really important in this case. So I think that's just about it. So just to summarize, I've presented to you a few hyperspectral imaging applications. Wasn't meant to be exhaustive. It was just meant to give you some examples of some of the things that I've been working on, where things are difficult, where things are straightforward. I outlined a couple of applications, including vapor plume imaging, surface imaging, where you're doing mapping or target identification, and then the surface contaminant application. And we talked about a few different modalities that I've had experience with, at least most of them. And then I tried to give you a couple of examples of application-driven sensor design and development, which extends all the way through functional testing, and some developmental testing is what we tend to drive towards on our programs, where we really want to show the capability against a simulated environment that's pretty close to how the customer will use it. And that's all I had. I can take any other questions.
Time for just 1 or 2 quick questions. Here, go.
You mentioned that you folks are looking at Raman spectroscopy. I don't know if those are small and feelable and rugged. Can you just comment on if that's possible to put in the field?
For Raman, so the receiver is small and rugged. That's the spatial heterodyne spectrometer. That's actually what we're working on now, is a deep UV system at 234 nanometers. The laser itself is not small. If you're familiar with the DARPA Luster program, it's one of those lasers. So it's difficult to get a lot of power down there, but as you probably know, there's some advantages to working down there. But our receiver is a spatial heterodyne spectrometer, and it's got all the benefits of high throughput, no moving parts, and that's working very well. But the laser part is always hard.
Thanks.
Yep.
So with standard hyperspectral push broom systems with a dispersion element, we have issues with smile, right? So
Yes.
spectral calibration at the edge of the.
Yep.
Because you're sweeping the DMD,
Yep.
you kind of immediately get rid of that, right?
I have smile, a
You
little
have
bit.
smile a little bit.
Yeah, or frown, whatever you want to call it.
Whichever way it goes.
Yeah, I mean, you still have some distortion at the edges of your field.
Right.
We can correct for it, but it's always better to not do it in the first place and correct for it.
And it seems like that almost depends upon the platform rotation about its axis too, right?
It could, I mean, I'm just talking about the static
Right.
image.
Right.
So I would say we have smile, we have keystone, and it changes based on the slit position. So I would say I mean, we worked really hard to control it, but it's more difficult than having one slit position over this field of view. The successor to this technology is a much narrower version, narrow field of view version of it that we're developing for the Air Force to do some ISR. And that is pretty good. Like, there's not much of either in that particular design.
Right, so I think there's coffee and cookies out front. Let's thank Julia once more.